All right, so in this lesson, we are going to move on to the subject of operators, right? And this is still going to be formalism, right? The whole point of this is the Dirac Formalism. But now the formalism is going to start teaching us about the things that really give the theory its modeling power, so to speak. Now, operators, I will name an operator T. T, as an operator, is a map from the vector space to the vector space. It's also a map, it can also be used as a map from the dual space to the dual space. But T takes vectors to vectors, right? And let's concentrate on these guys here. When I say takes the vector space to the vector space, obviously that means T, when it operates on a ket, because a ket is the element of our vector space, it's going to return another ket. Shouldn't even put a arrow there. And this is basically the defining relation. We've talked about a bunch of maps, right? We've talked about maps that take two vectors and return complex numbers. That's the inner product map. We've talked about a map that takes vectors and returns the complex numbers. That's a dual space mapping, right? A dual space mapping can be looked at as a map that takes a covector and a vector and returns a complex number. So these are both sort of related, right? In other words, if gamma is an element of the dual space, then gamma is a map that takes vectors to complex numbers. But you could also say, given an element of the dual space and a vector, you can get a complex number. So that would be a map that takes an element from the dual space, an element from the vector space, and returns a complex number. So you can kind of think of it both ways. But now we have a map that takes vectors straight to vectors. A map that we're missing, by the way, is complex numbers to complex numbers. Automorphisms of the complex numbers, for example. But that's not relevant to us now. Now, the obvious thing about operators is their linearity, right? That's the whole idea. These are linear transformations. I said that's the obvious thing. I don't know if that's so obvious, right? But they are understood to be linear transformations. And that's a huge subject of linear algebra, is the notion of linear transformations on vector spaces. And all of that stuff is sitting right here in quantum mechanics. It's the same thing. These guys are just routine vector spaces, routine complex vector spaces, and these are routine linear transformations of complex vector spaces. But what does that mean exactly? Well, it means if I have two operators, T plus S, one operator T and another operator S, I can define T plus S acting on a ket as the operator T acting on the ket plus the operator S acting on the ket. Remember, this returns a ket and this returns a ket. Two kets are in the same vector space V. V has a defined addition, right? We usually give it a little plus sign, but sometimes we can label the plus sign with a V, so we can get another ket. So this will be our ket B in the end. And there's a transformation to zero, right? A transformation that takes T acting on any ket gives you zero, and that's sort of the zero transformation. And it's linear over the complex numbers. So T acting on the ket C, where C is some complex number, A is equal to C times T acting on A. All right, so that linearity is really important. All these operators are linear. And I'll just say, of course, all these rules apply when T is acting on bras. Now, when T's acting on a bra, it's always acting from the right to the left. We'll never write T acting on a bra. That is not how we do it. And it would really ruin the flow of the notation if we attempted it, right? So we'll never write that. So everything that all operators acting on bras act from the right to the left. And whenever they're acting on kets, they always act from the left to the right. So keep that in mind. That's a really important notation. It's part of the overall scheme of things that makes this work smoothly, is to keep that convention in place, right? I mean, in principle, you could do without it if you tracked everything correctly, but this is that wouldn't be the Dirac formalism. That would be your own formalism. Okay, so now that we know that we're operating on bras and we're operating on kets, there is an important question to ask, which is, are these two objects, meaning the ket returned by this activity and the bra returned by this activity, whatever that bra is, let's call it C, are these two duals? Right? Are they duals of each other? Is B the dual of C? Now, there is a notation here that makes this a lot easier to talk about, but it has its own awkward problems. And Griffiths, in his quantum mechanics book, talks about this at length. But if I want to talk about the dual vector, meaning the bra that corresponds to the ket, that is the result of applying the linear operator T on the ket A, right? Right now what I have to do is I say, well, I'm going to call that resultant ket B, and the dual of B is B, right? So that's the dual correspondence. This ket B is the dual correspondent of that. So how do you can you find a way to write can we just refer to this thing and its dual? Like, maybe if I put it in parentheses and give it a special star, now I'm actually talking about the bra that corresponds to that. Of course, then we lose the sort of nice flip mirror symmetry issue. So that's really not a good solution. So what other solution can we do though, right? Well, it turns out what a lot of textbooks do here, and I'm only showing you this because it does come up in many of my books, and Griffiths mentions it at length as a problem, but as problematic, but it's really what we call an abusive notation. And you'll see the notion of we're going to abuse the notation, which means we're going to do something that's strictly speaking kind of outside the formalism, but it's obvious what we mean as long as we're all sort of on the same page. But abusive notation can confuse people if they're not on the same page. But this particular abusive notation is very, very common. And that is to say that the operator T is an operator, so it needs to operate on a vector. Well, that's a vector. A vector is a ket, right? The letter A is the name of the vector. Right? The name of a vector is not a vector. It's a name of a vector. And that's why I put quotes there. They're not scare quotes. When you talk about the name of things, you identify those. If you're talking about the name literally, you use quotes around it. When you talk about words literally, you use quotations around the words. The only way to make any sense of the operator's action is to put a vector on the right of the operator or a covector on the left of the operator. So we have the same issue over here, right? T operating on the ket A, like that. I'm the bra A, sorry. So, however, I could use the following notation. The ket that results from T operating on A, right? This is literally supposed to be in the same thing. I'm going to put a lot of equal signs there because we're not really defining it. It is abusive in a sense. The reason we say it's abusive is because TA doesn't mean anything. T is an operator, A is the name of something, and operators don't act on names, they act on kets. So only this can really mean something. However, this is so commonly done to mean this is the ket that results when you take T and you operate on the ket A, right? Now, I have no doubt that computer scientists have found a way to deal with this, right? Computer scientists are really good at using names and pointers and variables and all kinds of and all kinds of things. So this is probably a really, really old problem to them. In fact, if I looked it up, I could probably see exactly how they manage this. I'm sure there's programming languages that love this kind of stuff and have it just literally written right into the code. But the reason this actually is nice is because if I want to refer now to the dual of this or the dual of this, all I have to do is flip it, right? I just have to flip T, A, boom, and now I've got it. That is the vector that is dual to the ket that you get when you apply T to the ket A. So there is that advantage of being able to do this, right? However, I'm going to really try not to do it because Sakurai does not do it at all. He does not use this abusive notation, but many of my books do, or some of my books do. And Griffiths definitely calls this out and points out that it is actually awkward. The problem is I feel like Griffiths doesn't emphasize this utility of it, right? The reason that this is done is for this reason. Okay, but the question still is, what is this, the question that's on the table is C dual to B, right? Is T acting on the dual bra equal to T acting on the ket? Or I should say, is the operator T acting on the ket A equal to the operator of T acting on the dual to the ket A? Well, it's certainly not equal. I use the word equal. I should say the operator T acting on the ket A, is it dual to the operator of T acting on the dual of A? Now, let me just be really clear here. The answer is no, all right? So if you forget everything else, the answer is no. So the way we're going to go through this is we're going to define an operator where the answer is yes, and then we're going to eventually show why. So the way we do it in our formalism here is, in order that the ket, or let me see, how am I doing this? The bra that is dual to this ket is the bra you get when you act on the dual ket with a different operator. And that operator is called the Hermitian adjoint. And you can see what's going on here, right? In order for two kets to be dual, I'll remind you what the rule is. Right, so the rule was, if this is the ket expressed in a basis, its dual bra is expressed in the dual basis with these complex conjugated components. You know, I want to use bars for complex conjugation in this lecture if I can. So the way to guarantee that is to use the Hermitian adjoint of T. And right now that's just a definition. The Hermitian adjoint of T will always be dual to T, right? It will always be dual. And it will and the result of the Hermitian adjoint is going to be, let's see, I could actually kind of do it right here, right? I would say, let's say if T acting on B gives you A11, A22, then you can write, just as you can be guaranteed that T acting on the dual of B is equal to this, right? Oh, I'm sorry, geez, not T, T adjoint, right? T adjoint. Okay, so we're going to do a little bit more machinery, and then we're going to kind of prove this and get to that whole point about Hermitian operators. We're headed towards the goal of having Hermitian operators where T equals its own adjoint, and why that's so special and how that really makes our theory, gives gas to our theory. Okay, so understanding that those are not dual and Hermitian adjoints are dual by this definition, We will now proceed. All right, so say we wanted to build an operator. We want to build it from scratch, right? Now you can almost guess that this is going to have to do with the basis, right? The basis of our vector space. But but in this case, we can actually start talking about it without talking about a basis, right? Let's begin with we have our underlying vector space that models all states in quantum mechanics, and it's automatically canonical dual. And this, of course, is all of the kets, and this will be all of the bras. So now, I want to build an operator. Now, an operator is a map from V to V. Well, we'll consider it as a map from V to V, right? An operator T. So what's one way I might be able to build such a map, given what we have, right? We have a vector space and we have a dual space. Without anything else, how can we build such a map? Well, let me pick out, I'm going to show you a way to do it, right? We're going to first pick out one ket. I'm going to pick out a ket. I'll call that ket alpha. Go back to Greek letters there, alpha. And then I'm going to pick out a bra, and I'll choose the bra to be gamma. Yeah, heck, why not just be simple, beta, right? So I have alpha and beta. I have one ket and one bra. In my left hand I have a ket, in my right hand I have a bra. Now, I want to build an operator. What could I do with this ket and this bra to create a map from V to V? Well, if this thing's going to create the map, right, it's going to somehow be related to T. So T, according to my little theory, is going to take a ket, and it's going to take a bra, right? It's going to have a ket and a bra. Somehow I'm going to use those two. I'm going to build an operator called T. So this is some sort of like T is like a function of a ket and a function of a bra, right? That's where that comma is there. And that is going to operate on a ket, and I'll make the ket gamma. And it's going to return another ket, right? It's going to return another ket. So with just a ket and a bra, what can I do? Well, I could take the bra and my input ket, and I can get a real number, right? I can always produce a real number that looks like beta gamma, right? So that's a real number. And then what do I have left? Well, I have left a ket, alpha, so I can then just scalar multiply this complex number by alpha, and I have created a map that takes gamma to this new ket. And that's a ket, because remember, this is just a complex number, right? A complex number times a ket, it's another ket. And kaboom, I've done it. So with any given bra and a ket, I can produce a map from vectors to vectors using this prescription. I take the bra, I take the vector I want to transform, I calculate its inner product with the bra that I happen to drop out of the dual space, and then I just take that and multiply it by the ket that I just happen to draw out of the vector space. So not every necessarily yet, but I can make a transformation given a bra and a ket, right? And that transformation is called the outer product of alpha and beta. And it's written like this. With the ket on the left and the bra on the right. So that's completely, it's kind of oddly convenient because we're so used to putting the bra on the left and the ket on the right. The difference is this is a complex number. This is an operator, right? And the way we apply this operator is we apply it to an arbitrary ket, gamma, and you can see we use our beautiful notation here, right? And now I just say, oh, okay, well, I'm going to make that look like the inner product. So I'll just erase that. I'll erase the line, and I'll put the gamma ket there. This is a complex number, and this is the new ket, right? That whole thing is the new ket. So it's a really nice notation. And what's really nice about it in the Dirac formulation is I told you that operators can act on bras too, and you could easily do the same thing with a bra, right? And you get this guy, and the resultant bra is a scaled version of beta. So this outer product is a very, very important concept to get down. I got to admit, I never was very comfortable with it as a student. I don't know why, because it's not hard. I just don't think anybody ever kind of explained it the way I just did, where, hey, take a bra, take a ket. You can build a transformation. Now, you still have to kind of show that it's linear transformation. I'm not going to bother. It is. I'll just going to move on. But this counts as a transformation T, that object. So we now have three different ways. We can write a ket. We can write a bra. That's legal. If you see a ket or a bra sitting there, that's legal. And if you see a bra ket, right, that's legal. And now you know that this is legal also, right? This is a linear transformation. Okay, so now let's work with these linear transformations a little bit and see how useful they are. All right, now let's consider an operator T that is one of these outer products. I think we're eventually going to show that all operators can be expressed as an outer product. But we haven't done that yet, so let's just assume that this one is this outer product. Well, we can immediately blow up the states A and B, right? A and B is a ket and a bra that can be decomposed into the basis kets and the basis bras. So we're assuming an orthonormal basis. We always do, and we'll talk about why a little later, but let's assume an orthonormal basis. Not that it matters for this instance, right? We just break down we just decompose A and B into this. And so alpha I, and beta J, eigenstates J. And these are the two basis vectors. I said eigenstates, but I meant basis vectors. And then, everything commutes. Everything's linear, right? This is all about linearity as usual. So you get alpha I, beta J, and I and J, and this can always be understood as some single matrix element Tij with I and J. So this, and it's a double sum. So this linear operator is this double sum. And again, everything comes down to a basis. This is like almost like equivalent to a sort of a basis for all linear operators, right? And so the point being that we can reduce any operator written in the form of an outer product into this summation of the basis outer products, or outer products of the basis. So this is what this is supposed to look like: is T1 1 outer product with 1 plus T1 2 outer product 1 with 2, etc., etc., etc. And there you have it. So this is just an important step to take. Now, the next thing we want to say is, well, is this true for all operators? Can all operators be written like this? And that's an important question. Let's first look at something let's figure that out. So let's take the state alpha, right? We know that alpha can be decomposed into basis states. So I'll write alpha I like this, right? Now imagine that we map this using the dual space mapping with a basis vector J. In other words, I'm going to find the inner product of the basis vector J with the state alpha. So I do this on both sides. So I'm going to put that basis vector J over here. And remember, this is a ket, so I can find its inner product with any bra, and the bra I'm choosing is the basis vector J. Now, by linearity, I can immediately move this all inside, like so, and now you start to see, oh, this is again why orthogonality is important. This becomes the delta function of J and I, and so now I can write that the inner product of the basis vector j with alpha equals, this delta function is going to kill the sum and leave me with alpha j. And this is really, really important, right? This is you have to really get a sense of this. You can't understate the importance of this. Of course, in a system where everything interlocks with everything else, everything is sort of equally important, but you actually see this quite a bit. So the coefficient, or I should say the component of alpha, the ith component, meaning the coefficient of the ith basis vector, the complex number that's multiplied by the ith basis vector in its expansion, is equal to the inner product of the state with that unit vector, with the bra associated with that. Well, with that unit vector. If I say the inner product of the state alpha with the state j, what I really mean in my dual space language is the dual space mapping of A with the bra associated with j, right? But this is a complex number over here. This is a complex number, and this is a complex number, so the equality makes sense. But we have to now understand that this is the jth component of the vector alpha in this basis, right? The basis given by j equals 1, 2, 3, or 4. So that it turns out that's going to ultimately be our connection between all of this and wave mechanics. Okay, but that being the case, well, that means, right? That means that I can form the following object. Well, I don't know about forming the following object. Let's put it this way. I could have written, I guess let's go back and erase everything, right? Let's go backwards. Let's go backwards. I can get rid of all of this, get rid of this, get rid of that, right? So we're back to where we kind of started, right? But now I know what alpha I is. I know what alpha I is because I just did a symbolic method, a formalism. This is why it's called formalism, right? It kind of looks formal. So first of all, I swap I with alpha I, right? And then what do? Well, then I take that alpha I and I replace it with what we just calculated, which was I alpha, right? No, I don't like my alpha. I alpha, like that. And that's completely legit because this actually equals, this thing here actually equals alpha I. In fact, the equality is so strong you can almost say it's a definition almost. I think we showed that it's not, because it really depends on it depends on I being an orthonormal basis, for example. So I guess it's not quite that strong. But the point is this makes perfect sense. That's a complex number. That's a vector in the vector space. That's a ket. You can multiply kets by complex numbers all day long. So now that I know that alpha equals this, the beautiful thing about the Dirac formalism is that it's totally associative. And I can actually treat this differently. I can write this as the sum over I of the operator I, right? And that's an operator we just showed, but this is a sum. So this is a sum of all of these basis ket constructed operators. That is an operator, right? In the very same vein that that this is, right? Right, except Tij, right, for the one operator I just built, Tij equals delta Ij, right? If you replace Tij with delta Ij, you literally get this object right here. You eliminate one of the sums. So, with that in mind, that operator acts on alpha. So I'm thinking of an operator acting on alpha. But look what I've got, right? I've got an operator acting on alpha, and then I've got alpha over here on the other side of the equal sign. So this operator clearly doesn't move alpha at all. This operator is equal to the identity operator. And that's the lesson we're learning from this. And you can't, as Sakurai says, you can't overstate how important this is. The identity operator, right? The operator that takes any ket and returns the same ket. That operator can be written as the sum over all the basis states of the outer product of every basis state with itself. This is a literal restatement of the identity operator. Those two are the same. Whoops. Of course, the way I wrote it was lame because you still need an alpha over here, right? The point I keep saying a million different ways that equals I, right? So that really, really, really important, right? And we derived that just from, look where we started. We just started with this, and then we found the outer product, or the inner product, I'm sorry, of this with, not I, but J. And that inner product was what drove us to become aware that we can write the identity operator as this sum. Okay, so from now on, whenever we want, we can insert the identity operator almost anywhere in our work. And that means we can always insert a sum over some dummy variable, but it must be over all of the basis states, right? That's really important, right? This sum is over all the basis states I. So this identity operator, it's an infinite sum if you have an infinite number of basis states, which you probably will. And this can be inserted anywhere you can insert the identity operator. And I think there's a word for this. It's called the completeness relation. This is called the completeness relation. It's called the completeness relation. So that's the completeness relation, very, very, very important. Okay, so now let's exploit that and learn something new. All right, let's consider any operator T, right? I was just talking earlier about operators of T that can be sort of described as the outer product of a ket and a bra, right? But now I'm going to consider any operator at all. So now I've got that operator. I certainly know that operator is going to be unaffected by multiplying by I. So this is an operator here, and I is the identity operator. And operators can be multiplied, right? This is linear algebra we're talking about, right? This is a linear transformation on a vector space. You can multiply those linear transformations by each other and get another linear transformation. I'm not going to go through all that matrix math that proves that point, but it is something you should know. So I can immediately write this as the sum over all the basis states, I times the operator T, right? These are literally the same thing. And then I can take this guy and I can multiply on the right by another copy of I, right? Another copy of I. And that copy of I is going to be another sum over a different over this all the states, J, like that. And now everything, these are all linear operators, right? So I can definitely turn this into a double sum, I, J, and then I have I like this. I have I here. We have the operator T, and we have J and J. And then just to be a little bit tighter, I've written it out this way, but we're going to now be a little more suggestive and just put the T, put the T here, J, right? So now what are we looking at here? What are we looking at? Well, what is this guy, right? We see there's definitely a leftover ket. There's definitely a leftover bra, right? The guy in the center, though, remember, I, T, J. Well, T acting on J is just another ket, and a bra acting on a ket is a complex number. So this whole thing is a complex number, right? It's really important to be able to see where these complex numbers are. That's the only way this makes any sense. So that's some complex number, which I'm going to call Tij. And that's going to be the same thing. I'm defining it that way. This is definition. right? It's a simple complex number, so I just give it a name, Tij. And then, of course, what do we have? We have the sum over ij of Tij times the outer product I with j. And so my arbitrary operator is written as a sum of outer products of all of the basis vectors times some coefficient. That coefficient is this guy right here, which is always called the matrix element. The matrix element of T. Well, T has many matrix elements, right? One for every I and every j. But this is a matrix element of T. And that matrix element, it's usually written out like this. You know, it's not as often written out like that, but just for illustrations, the point I'm trying to make is this applies to every linear transformation, not just the ones that can be written in this form. So what I've now shown is that I can take any linear transformation and, I can write it in this form, right? Because I could blow this up into, I can find an alpha and beta that will always satisfy this, right? So there you have it, right? That's how you decompose T into these outer products. And it's going to be these matrix elements times the outer product. Okay, so, and notice how we did this. We did this just by using this completeness relation, which was so important. All right, so what's next? Well, let's end the lecture by just a quick review. We've studied the question of operators. We were going through the formalism of operators, right? Maps from vector space to the vector space or the dual space to the dual space. I've really emphasized it this way. Most books do, but they work just as well in both directions. And we defined how they create new bras and new kets. And we discussed the definition of the Hermitian adjoint is the operator that produces the dual as specified here. Let's see if I can get the language right. An operator acting on the ket A is dual to the adjoint of that operator acting on the dual of the ket A, which is the bra A. Right? That's called the Hermitian adjoint, and it'll reproduce our definition of an adjoint, meaning that the operator acting on B gives you some new ket, which in this case we're giving coefficients or components the label A, and the dual of that is this by definition, and by definition there's an operator out there called the Hermitian adjoint, which acts on B and gives you this. And then we talked about building an operator, and we talked about how if I take a vector and a covector, I can always build an operator with a very simple little formula. I just combine the bra with the ket I want to transform, get a complex number, and multiply that by the ket that I pulled out of the vector space. So it's very easy to write operators if I have a bra and a ket lying around. And of course, I have a lot of them lying around. I have a whole infinitude of both of them, one representing all the physical states of the system, and the other representing the duals of those physical states. And then we took that, and what we did was we showed that I guess we described the completeness relations. That was really important. We invented the completeness relations. That's the big takeaway, I guess. And we also showed how, I think we showed one of the, we showed how every operator using the completeness relations could be expressed in this form. So what's left to talk about? Well, we certainly need to talk about Hermitian operators. That's really, really important. And we also need to talk about I think Hermitian operators is next. So what we'll do is in the next lesson, we'll talk about Hermitian operators, the eigenvalues and the eigenvalues of Hermitian operators, and how they produce for us a complete basis set for our underlying vector space. Okay, thank you very much, and we'll see you next time.